Welcome back to Physics 142. We're working our way up to Ampere's law, and to do that, in the last video, we spent a little bit of time reviewing integrals over some sort of path. So the path that we were specifically interested in for thinking about Ampere's law, which we'll get to in just a second, is we're interested in thinking about paths through magnetic fields. So we think about having some sort of magnetic field and walking along some path, maybe some distance, maybe 10 meters this way and 10 meters this way, walking that path through a magnetic field. And specifically, when we do this integral, what we do is we're going to take the dot product between B and dl. Remember, the dot product is such that if you're going the same way, right, if you have two vectors that are going the same way, so if my path is along the magnetic field, then that's going to contribute, right, that's going to be plus 1, right? We end up getting a cosine of 0, which is 1, so that's sort of all of it counts. All right. Whereas if you go perpendicular to the line, you get 0 contribution, right? So that's what we were doing last time, is we sort of introduced this path integral. And now I want to sort of understand is why is this path integral important? But to do that, we have to go back and think a little bit about things that we learned about electric fields before we think about magnetic fields. And so what are some things that we learned about electric fields? Well, we learned how to produce an electric field, and what we realized is that charges are things that produce electric fields. And so we were able to write that down in a formula. All right, we wrote down that E is the integral of k dq over r squared, and that ends up being in the radial direction, the r hat direction. Basically what this says is for every little piece of charge dq, we create electric field, right? So we have charges here are the sources of electric fields. And this, we maybe give it a name, we called it Coulomb's law. All right, so I'll just note that here on the side. Let's call this Coulomb's law. My spelling here. Can't remember how to do all this. All right, there we go. C-O-U-L-O-M-B-S. There we go. Coulomb's law. All right. But we had another way too where we could calculate magnetic fields, and that was through, electric fields, and that was through Gauss's law. All right, and so another way that we realized that sort of charges produce electric field is we had this relationship we called Gauss's law, and there we took a surface integral where we found the flux through some surface, all right, and we realized that that was related to how much charge the surface enclosed. And so I want to just, really make sure we can understand Gauss's law conceptually here and understand what's going on with it, all right, is the idea with Gauss's law is that here, this is the flux through a closed surface. So we imagine some sort of surface, right? And we basically think about how much electric field is going through that surface. And well, that's going to be related to how many sources of electric field do you have, right? Q's, charges, produce electric field. So if you put more charges inside that surface, you'll get more electric field coming through the surface, right? So we can think of this as the sources of electric fields. Right, and these equations are fairly similar in that here, the dq's, right, we can think directly, well, how much charge produces an electric field, you could calculate it directly, or Gauss's law, well, that lets us calculate a flux, and we used that because sometimes it was a useful shortcut. All right, so I'm going to need a little more board space now, so I'm just going to go ahead and move this up here so that we can really flesh out this comparison. All right, and so for Gauss's law, right, the reason we used it is it was a shortcut, right? Let's write this down. It was a shortcut to finding E fields, right? Where, there's an E here, so you can calculate E fields when the charges were distributed in a way that there was a lot of symmetry, right? So we might say when the charge distribution had high symmetry. All right, so if we had a symmetric situation, something with spheres or cylinders or planes, right, if there was a lot of symmetry, then we could use this to find electric fields, and some of you did that successfully on your exam, and feel free to look back and review the videos on Gauss's law about how we're able to do this. But basically, if we knew something about the Q enclosed, and if we knew we had symmetry, we're able to find electric field. And it was sort of a shortcut to doing sometimes these really nasty integrals where we had to add up all of the different charge in some sort of distribution. The other thing I should mention about Gauss's law is that it's really important to recognize that to do this, what we would do is we would imagine a surface, right? We'd have this closed surface that we were calculating the flux through, right? We're doing this surface integral over some sort of imaginary Gaussian surface. So I might mention here that this applied, right? Gauss's law applied for what we call a Gaussian, right? Surface, or maybe I might call that an imaginary surface we chose, right? So we would get to choose our Gaussian surface, and then Gauss's law would apply over that surface, right? This idea that the amount of charge inside, all right, was related to the flux through the surface. And so I point all this out because what we're looking for is sort of similarities here in magnetism. All right, so in magnetism, we realized it's not just charges that create electric fields, but it's moving charges that create magnetic fields. All right, so charges create electric fields, moving charges create magnetic fields. Did I say that wrong? Let me just say it clearly, right? Charges create electric fields, moving charges create magnetic fields, and we represented that, we've talked about that, was this thing called the Biot-Savart law. All right, so let's write that down. The Biot-Savart law. All right, in the Biot-Savart law, let us calculate magnetic fields, right, how much magnetic field we had, and specifically, that said, well, magnetic field was this mu naught over 4 pi, and then we'd integrate the amount of current, right, IDL, and then we'd put in this little r hat cross product because you had to get a perpendicular vector in there, right? The direction is perpendicular divided by r squared, right? But specifically, the important thing here is here we have currents, which are sources of magnetic fields. So just like charges are sources of electric fields, moving charges or currents are sources of magnetic fields, all right? So that was the Biot-Savart law. And so Ampere, but it turns out there's another way that we can calculate magnetic fields, how much magnetic field you're getting. And so that is going to be sort of the equivalent of Gauss's law, and that is this thing called Ampere's law. Ampere's law. So that's what we're working up to here, right? So just like the Biot-Savart law lets us directly calculate magnetic fields from moving currents, all right? And that's the sort of analog to this Coulomb's law here, right? Where we're directly calculating electric fields from charges, right? Ampere's law is sort of going to be a shortcut to finding magnetic fields, all right? When we have high symmetry. So let me write it down and then we'll think about it a little bit. So Ampere's law says the following, all right? It says that if we take a closed integral, b dot dl, and specifically, this is over some sort of path, all right? This is over a closed loop, all right, or a closed path. So this is, we're gonna walk in some loop, all right? So just like we were doing in the previous video, right? BDL means we're gonna walk through a magnetic field over some path, and specifically if it's a closed path, so that means you get back to where you started, all right? What Ampere's law says is that if you take that integral, b dot dl, all right, that will end up being equal to mu naught times the current enclosed within your loop. All right, so this is the current going through your loop. All right. So, and what do I mean by that? Maybe I should sketch a little picture. All right. So if I have some path that I've walked, all right, and you could imagine that I have some wire coming out of the page. All right. So here's wire coming out of the page. All right. Whatever wires I put in here, right? So maybe here's another wire, right? Or here's another wire. All right. So the amount of current going through the loop ends up being equal to, times mu naught, ends up being equal to the path integral if I walk all the way around this path, all right? So if I have 3 different i's, right, this would be 3i worth of current, this path integral would end up being mu naught times 3i, all right? That's what Ampere's law says. And so what we're doing here, just to be clear, is we're connecting sources of magnetic fields, that is current, to something that we're imagining. Specifically in this case, all right, we're going to imagine not a surface, like with Gauss's law, right? There we imagined a surface, but now we're going to imagine some paths that we want to walk around. So I should say, you know, here, just like this applied for a Gaussian surface, all right, this is going to apply for what we might call an Amperian loop, all right, which is going to be an imaginary path that we choose, all right, an imaginary path that we choose. And I should also mention that, you know, the reason that we'll be interested in Ampere's law is just like with Gauss's law, Gauss's law was sort of a shortcut to finding electric fields when there was high symmetry, all right? Ampere's law is going to be a shortcut to finding B fields, all right? Magnetic fields when we have high symmetry. So I'll want to do some examples of these, and so we'll do examples of Ampere's law in the next videos, but hopefully this really helps lay it out here for you, all right? Just like in electricity, the way we calculated our electric fields was either directly from the charge or indirectly by imagining this surface enclosing all of that charge. All right, for magnetism, the Biot-Savart law lets us calculate magnetic fields directly, versus Ampere's law is going to let us imagine some path that we walk around currents, all right, and use that to sort of more indirectly calculate B, all right, calculate magnetic field when we have high symmetry. So stay tuned, and we'll do some examples of this in the next video.